Welcome to The Explainer. Today, we're diving into a really fundamental question about quantum mechanics. You know, the kind of question you've probably had yourself but maybe felt a little hesitant to ask. Let's get right into it.
Yeah, think about it. How can we possibly build theories and write these incredibly precise equations about a world that's totally invisible to us? A world we can't touch, we can't feel, we can't sense in any way we're used to. It's a fantastic and very fair question.
And you know what? The research we're digging into today actually calls this a deep and honest doubt. And that's exactly what it is. So instead of just brushing it aside, we're going to unpack it together, step by step. No weird mysticism, I promise.
All right, so to kick things off, let's get right to the heart of the problem. What is it exactly about quantum mechanics that feels so impossible to grasp?
It really boils down to this. You know, in the physics we learned in school, we can see a ball flying through the air. We can feel the force it takes to push a box. There's a connection. But in the quantum world, there's nothing for our senses to grab onto. It feels like it's all just abstract math. So how in the world can anyone really claim they understand it?
And this doubt often gets a little boost from the common analogies we hear. Like, if a qubit, the basic building block of a quantum computer, is just a fancy coin flip, well, we already get coin flips, right? Why do we need this whole mind-bending new field of physics for that? And that is the absolute perfect question to ask. It gets us right to the core of a huge misunderstanding.
To really answer that, we first have to tackle a huge assumption we all make. This idea that we absolutely have to see or touch something directly to be able to understand it and predict what it's going to do.
I mean, think about it for a second. You use your phone and your Wi-Fi all day, every day, but have you ever actually seen the electromagnetic field that makes it all work? Or how about this? You're watching this right now on a device that is crunching billions of calculations per second, but you've never touched or felt or heard a single one of those CPU instructions.
And today, we can actually detect ripples in space-time from black holes colliding billions of years ago, but you for sure never felt a gravity wave pass through your body. And yet, we completely trust the science behind all of these things. So why?
It all comes down to this one single, beautiful rule. This is the bedrock of all modern science. It doesn't matter if you can see it, or feel it, or even wrap your head around it. The only thing that matters, the only criterion, is whether our mathematical predictions consistently match what we see in our experiments. If they match, we're on the right track.
Now, this is so important to get. Quantum theory wasn't just invented for fun by some bored mathematician. It was literally born out of a crisis. Because the old physics, the physics of our everyday world, it just broke.
As we got into the late 19th and early 20th centuries, scientists started running all these experiments that gave results that made absolutely no sense. Classical physics couldn't explain why hot things glow the way they do, or why different elements give off light in very specific colors. The old rule book was failing, right there in the lab.
So the main takeaway here is that quantum mechanics wasn't just pulled out of thin air. The math was forced into existence by the raw data from experiments. It's not a fantasy, it's just a way of describing the patterns we actually observe in nature.
And that brings us right back around to that coin flip. If experiments forced us to create this whole new kind of math, there must be something fundamentally different about it. So let's look at exactly why that coin flip analogy is so misleading.
Okay, check this out. For a normal coin, its state is about our ignorance, right? It's either heads or tails, we just don't know which one yet. But for a qubit, its state is about potential. But the real mind-blowing difference is the logic. Classical probabilities just add up, simple. But quantum mechanics uses something called amplitudes. You can think of them like probabilities, except they can be positive or negative. And that means they can interfere with each other. They can add up to make something more likely, or they can completely cancel each other out.
And that right there is the whole ballgame. This ability for possibilities to literally cancel each other out to zero, that's called interference. And it's something that just cannot happen with a normal coin. You can't have a negative 50% chance of getting heads that cancels out the positive 50% chance. It makes no sense in our world. This unique behavior is exactly what quantum theory was built to describe. This also helps us bust that other common analogy that a qubit is like a byte that holds all its values at once. Nope. A classic byte holds one definite state. A qubit's state is all about potential, a whole sphere of possibilities. But, and this part is critical, you can't peek at all those possibilities at once. The instant you measure a qubit, the whole system collapses into just one single outcome. So a qubit is absolutely not a form of parallel memory.
So, okay. If we can't really visualize quantum theory, and qubits aren't just tiny little parallel processors, then what's the point of all this strange, counterintuitive science? Well, the point is that nature basically forces it on us. We have no choice. You simply can't explain why atoms are stable and don't just collapse on themselves without it. You can't explain chemistry or how semiconductors and transistors work in, every single electronic device you own. Lasers, MRI machines, even the time corrections that make your GPS accurate, all of it relies on understanding and using these quantum effects. And that leads us to the final and maybe the most important shift in thinking we have to make. We have to be willing to let go of our everyday intuition. Quantum theory is not a story about what is happening in some tiny invisible world. Instead, it's a powerful tool. It's a set of rules that tells us what we can predict and what we can control. It doesn't give you a picture of what's going on, it gives you a recipe for predicting the outcome. And it turns out, that's all you need to power the entire modern world.
So in the end, we don't need to see the quantum world to understand it in the only way that truly matters, being able to predict its behavior. And that leaves us with one last thought to chew on. What other invisible worlds are out there, just waiting for us, not to be seen, but to be understood through the powerful lens of prediction and experiment?